Hi students, now in this lecture we will discuss about the carbanions. Carbanion is actually a carbon with a negative charge, and we see here it has 8 electrons in the valence shell. And this carbanion is formed when suppose an atom A is lost from the carbon, the bond breaks here, and the atom A goes with as A plus without electrons, and the carbon now acquires a negative charge. So this is a heterolytic bond fission which occurs here, and the carbon with negative charge is called as a carbanion, and it's a very common intermediate in most of the organic reactions. Regarding this hybridization and the shape, we know carbanion actually it resembles with the ammonia because it is isoelectronic with the ammonia molecule. So carbon, it has 8 electrons here, nitrogen, in the ammonia molecule here you see there are 3 bond pairs and a lone pair, so total number of electrons are 8. So 1 lone pair, 3 bond pairs. So same situation here also with the carbanion, 3 bond pairs and a lone pair. That means it resembles with the ammonia. And we know the ammonia has a pyramidal shape, correct? So it has a pyramidal shape. Carbanion also has a pyramidal shape, and the hybridization is sp3. Now regarding its stability, which is the most important point, okay, this is what actually we are going to discuss here. The stability of the carbanions, right? We know the carbon is actually an electron rich molecule, right? And these are the different types of carbanions. This is a tertiary carbanion here, 3-degree carbanion. This one is a secondary carbanion, and this is a primary carbanion because it has only one alkyl group attached here, and it has 2 alkyl groups, it has 3 alkyl groups. Carbon is electron rich, it has a negative charge, and therefore if you attach a group which can donate electrons to the carbon, that will increase the negative charge and that will make it unstable. So we get the conclusion here that if you attach an electron donating group to a carbanion, that will increase the electron density as a carbon and will make it unstable. But if you attach an electron withdrawing group, right, not electron releasing but rather electron withdrawing, a group which can withdraw electrons from the carbon, that will decrease the electron density, that will decrease the negative charge on the carbon and make it stable. So because of electron donating groups, the carbanion becomes unstable, and electron withdrawing groups, it makes it stable. So that's why in the tertiary carbanions there are 3 electron donating groups, and we have a positive effect for all these groups. They donate the electrons, that will increase the negative charge, and hence it will be the least stable. In the secondary there are only 2 alkyl groups, 2 R groups here, 2 methyl groups here, right? So the electron density in comparison to the tertiary one will be less. So alkyl groups, which are electron releasing groups actually, right, these are the electron releasing, or you can say electron donating groups, because they have the plus I effect, they have the positive inductive effect, they donate electrons, they will make this carbanion unstable, right? In the primary there is only one alkyl group, so therefore the tertiary one is more stable than secondary than the primary. However, if you have a carbanion and if you attach a group which can withdraw electrons, right, which can decrease the electron density on the carbon, that will make it stable. Say for example we attach a nitro group here, NO2. Any group which can withdraw electrons from here, that will make it stable. Or suppose you attach any halogen to here, right? So if you attach a chlorine here, it will withdraw electrons now from the carbanion, and it will make it stable. So electron donating groups, they decrease the stability, while as electron withdrawing groups, they increase the stability. That's why the stability order, the decreasing stability order is, right? So the 1 degree is more stable than secondary than the tertiary. So you can say the decreasing order the decreasing order of stability. Hi students, now let's discuss about the carbanions in this lecture. We know the carbanion is carbon with a negative charge, and it has 88 electrons in the valence shell. It's formed actually when suppose we have a carbon attached with atom A, and for example the heterolytic bond fission occurs such that both electrons they remain with the carbon and atom A is lost as A plus ion, right? So now what you get? You get a carbon with the negative charge. So this carbanion, which is electron rich molecule, it has a negative charge, it has 8 electrons in the valence shell, right? This carbanion actually resembles with the ammonia. It's isoelectronic with the ammonia. So therefore the shape and the hybridization can be compared with the ammonia. We know that in ammonia molecule there are 8 electrons. You can see here there are the 3 bond pairs and a lone pair. The carbanion also has the 3 bond pairs and a 1 lone pair, 1 electron pair there. So therefore it's an isoelectronic species, right? So these are the isoelectronic species, carbanion and ammonia. And ammonia, we know it has a pyramidal shape and it has sp3 hybridization. So same will be with the carbanion, sp3 hybridization, and the shape is trigonal pyramidal. Now coming to the next important point here, that is about the stability of the carbanions. See, the carbanion is actually the carbon with a negative charge. It is electron rich, right? It has a negative charge. Because of negative charge, it is unstable, right? And if you can decrease that electron density on the carbon, if you can decrease the negative charge on the carbon, it will be slightly more stable, right? So therefore, if you attach suppose the groups which can withdraw electrons, electron withdrawing groups, they will decrease the electron density and they will make it stable. But if you attach electron donating groups, or you can say electron releasing groups, right, a group which can donate electrons to the carbon, to the carbanion, that will increase actually the electron density. The electron density will increase at the carbon and it will make it unstable. We know that there are different types of carbanions, primary, secondary and tertiary. Here this is the tertiary carbanion, this is the secondary carbanion, and this is the primary carbanion. In tertiary there are 3 alkyl groups which are electron releasing groups. They have the plus I effect, positive I effect. So you can say these are the electron releasing groups or electron donating groups, because they have the positive I effect, they have the positive inductive effect. They donate electrons and that will increase the negative charge in the carbon, right? And therefore it will be the least stable. If you look at the primary one, it only has a 1 alkyl group, 1 group which can donate electrons. Here it has 3, the secondary has 2, right? The secondary has 2. So therefore the most stable out of the 3 is the primary one. The primary one should be the most stable, and then the secondary, then the tertiary. So I think the stability order will be in this order, right? So the decreasing order, we can say the decreasing order of the stability, right? The stability order for the carbanions is 1 degree is more stable than secondary, than tertiary, right? Because in the 1 degree there is only 1 electron releasing group, and we know that electron releasing group increases the electron density on the carbon and it will make it unstable, right? So that is why we find that 1 degree is more stable, because it has only 1 electron releasing group. Higher the number of electron releasing groups, lesser will be the stability, right? So if you have the higher number of electron releasing groups, lesser will be the stability. So the most stable one is, I think, here the primary one out of the 3. And if you attach a electron withdrawing group to the carbanion, right? Suppose a group which can withdraw electrons, which can take electrons away from the carbon, it will decrease the negative charge and it will make it more stable. It will make it more stable. So any group which has a negative I effect, which is electron withdrawing group, that will increase the stability of the carbanion, right? So that means if you have say for example a CH2 negative charge, right, CH2 negative here, if you attach a chlorine to it, which is electron withdrawing group, and it will make it more stable, right? It will make it more stable. We'll do some questions on this later on. Okay, fine. So we got the point. Electron releasing groups, they decrease the stability. Electron withdrawing groups, they increase the stability of the carbanions. And the stability order, the decreasing stability order for the carbanions is 1 degree is more stable than secondary and tertiary. I think this is opposite to the carbocations. In the carbocation, the tertiary is more stable than secondary and primary. So that means the order of stability for the carbocations and the carbanions is opposite, right? Fine. Next point is carbanions can also be stabilized by the resonance. If there is resonance, we can say it's more stable, right? So resonance can also stabilize the carbanion. Okay, so resonance delocalizes. Here it is the positive, or we can say that it also, the resonance delocalizes the positive charge as well as the negative charge, right? Like the resonance can stabilize the carbocations. Similarly, resonance can also stabilize the negative charge, but that means it can also stabilize the carbanion. So resonance effect is same for the carbocations and the carbanions. In the previous video, we have discussed that if you have a carbocation like this, and if there is a conjugation, if there is a carbocation at the allylic position, then the carbocation can be delocalized, right? Can be delocalized, right? So the carbocation can be delocalized there, but the electron density ring will be in this direction. So the electron density, the pi electrons will move in the direction of a carbocation which is electron deficient, and this pi bond will break and it will shift here, and you get another canonical structure like this: CH2 single bond CH, then a double bond CH2 here, and then the positive charge is over here. So like the positive charge is delocalized, we can delocalize the negative charge as well, but the direction of the flow of the pi electrons is a little bit opposite in the carbocations and the carbanions, right? Because the carbocation is electron deficient, so pi bond, when it breaks, it shifts in the direction of a carbocation. Whereas in the carbanion, in this example here, the electron pair, the pi bond will move away from the carbanion, and you get a double bond over here. And the next resonating structure that you can find will be CH2. Here the negative charge is, and then a single bond CH, and then a double bond, and then it goes back here, and you get the first one back. So that means resonance has the same stabilization effect for both the carbocations and the carbanions. Resonance can stabilize the carbocations and the carbanions also, because it can delocalize the positive charge and also the negative charge, and therefore it provides the stability. So higher the resonance in the carbanions or carbocations, more will be the stability, right? So let's take another example of this one, another carbanion. If you attach a benzene ring, right, we know there is a carbanion here, carbon with negative charge, and then there is a single bond, then a double, single. So you attach a benzene ring, an aromatic ring, which is alternate single and double bonds, and the negative charge is at the allylic position to this one, right? So therefore it can delocalize here. So this electron pair can delocalize, it can go down here, and it will go in this direction. So let me draw the different canonical structures for this carbanion also, right? So the resonance can delocalize the negative charge, and it also provides the stability, right? So that means the first structure that you can expect here is, you have a carbanion here, and you actually have the alternate single and the double bonds. Now what will happen? The electron pair will shift in this direction, it will move here, right? And then the next canonical structure will be like, it will look like this. The negative charge here, it forms a double bond. The ortho position gets a negative charge. There will be a double bond, here will be the double bond. So the structure number one, first structure, it changed to the second structure. And then you can further delocalize this one. If you get this electron pair down here, forms a double bond, and this electron pair shifts over here, or the para position, and the next canonical structure will be like this. You get a double bond here, double bond over here, and the negative charge on the para position. So this is the third canonical structure, right? Again, I can delocalize it. It goes down, and it is this one. It goes again on the ortho position, right? And you get a structure like this. You get a double bond over here, you get a double bond here, a double bond here, and a negative charge on the ortho position, right? So again, then I can change it into the first one back, the fourth one, right? It can change, you can change it into the fourth one back. It goes up, it goes down, and forms the double bond here. So inside the ring there are 3 double bonds, and now you got a negative charge on the same first carbon. So that means we got the negative charge delocalized over the ring at the ortho position, right, at the para position, and again the ortho position, right? So that means if you attach one ring, one benzene ring, the negative charge gets delocalized over the ortho, para, and the ortho position. So total number of canonical structures we find here is 4. So that means this provides a lot of stability. If you attach a benzene ring, the benzene ring provides a lot of stability to the carbanions. And higher the number of these benzene rings, if you have suppose 2 phenyl rings, then the canonical structures will be more, right? One benzene ring provides how many canonical structures? 3, right? You get a negative charge on the oxygen, sorry, at the ortho position, at the para, and the ortho. So 2 ortho, 1 para. So one benzene ring, you get 3 canonical structures in addition to the original one, right? So total is 4, correct? So one benzene ring provides 3 plus the original one, so that is 4. If you have 2 phenyl rings, suppose you have a carbanion here, okay, you got a carbanion here with the 2 phenyl rings. Here the 2 phenyl rings here, carbanion like this. One benzene ring actually can provide 3 structures, this one 3 plus the original one. So total number of canonical structures for this one, for the biphenyl carbanion, is 7. So that's why the biphenyl is more stable than the phenyl carbanion. If you have a triphenyl, right, if you have 3 phenyl rings, 3 benzene rings attached to the carbanion, and how many structures you can expect from this one? I think we can expect first here from 3 here, 3 here, 3 here. So total is 9, 9 plus the one original one, so there is 10. So total number of canonical structures will be 10. So that's why the triphenyl is more stable than biphenyl, and the biphenyl is more stable than the phenyl. So higher the number of resonating, these phenyl rings, more will be the stability, because there is more delocalization and the negative charge gets delocalized more. So therefore it provides more stability, right? So resonance provides stability. Electron withdrawing groups, they also provide stability. Electron releasing groups, they decrease the stability, right? Now we can write down the overall order of stability for the different carbanions, right? So first one is the aromatic one, right, the most stable one. Then a resonance, but a simple conjugation without any benzene ring. Allylic carbanions, right, these are called allylic carbanions. This is an aromatic carbanion. Aromatic carbanions are more stable than allylic. You also find the resonance here also, but the benzene, it provides more stability, right? So aromatic carbanions are more stable than allylic carbanions, and then these alkyl carbanions. And among the alkyl carbanions, we know the stability. If there is more, higher the number of alkyl groups attached, less will be the stability. That's why this one is most stable among the alkyls. Why? Because it only has the 3 hydrogen atoms. And if you attach a 1 methyl group there to this carbanion, it will provide instability, right? It will donate electrons, so it will be relatively more unstable than the secondary, then the tertiary. So tertiary is the least one, okay? This is the least one, least stable, okay? Correct? So then let's take some questions here. You have 2 carbanions over here. Suppose we have a carbanion here, right? The negative charge is over here and over here also, right? Carbanions. The first one here is more stable than the second one. Reason because both have the benzene ring. The difference is only we have a nitro group which is electron withdrawing group, and the methyl group is electron releasing group. And electron withdrawing group right, electron withdrawing group, and this is the electron releasing group, or you can see electron donating group. Okay, electron releasing group, electron withdrawing electron donating group here, it will provide it will make it unstable, but electron withdrawing group, the nitro which withdraws electrons, it provides more stability. Right, so that's why the first one is more stable than the second one. Right, let's take some other questions as well. For example, let me write down here some of the carbanions. If we have a CH3, CH2 negative here, this is a primary, I think, right? Let's say this is the first one, and let's take the another one, the CH triple bond, right? Carbon, and the third one is CH2 and CH, like this. Among the three, what will be the stability order? You see, all of them are 1 degree, right? Everyone is 1 degree. This is the primary 1 degree. This one is also 1 degree carbon, and this one is also 1 degree. So how we define it? How can we differentiate the stability? Is there any way to look at it? Yes, there is. Actually, the hybridization of this carbanion, right? This this carbon is actually sp3 hybridized, but this one actually is sp hybridized carbanion, and this one has a hybridization of sp2, right? This one is sp2, and here you find the s character more, right? Here is the more s character, here is the 50% s character, and there is only 1/3, and there is 1/4. More the s character means more stable, right? Because the carbon with higher s character is more electronegative, it can bear the negative charge, so therefore the B1 is more stable than the second and then the third. Therefore the order of stability will be B is more stable than C and then A. This is the decreasing order, because higher s character means the carbon with negative charge will be little bit more electronegative, right? Because electronegativity, it also depends on the hybridization also. Okay, so the sp hybridized carbon, actually sp hybridized orbital has a more s character, which is actually more closer to the nucleus, right? More penetrated towards the nucleus, so it is held strongly by the nucleus, so that's why this one is more stable. The B is more stable than the C, than the first one, and that's why this acetylene, it is actually derived from the acetylene. That's why this is acidic. Out of the three, alkanes and alkynes, the first one, the acetylenic hydrogen, is more acidic because it has a more S character, like this CH. If you have a CH triple bond CH, okay, so this is ethyne. Actually it has some acidic character, right? So it dissociates into CH triple bond C negative there, and the H plus ion. So this one, the conjugate base, right? This is the conjugate base. This conjugate base is more stable than any other conjugate base from the alkenes or the alkanes because of the more S character. So it has a 50% S character, right? 50% S character, and we know that more S character means more stable carbanion, right? So that's why this is more stable. So let's take some more questions here, some of the quick examples here, right? Okay. For example, let me draw a structure like this. This is the one. Let's have another carbanion like this over here, the carbanion, right? And then let's see, we have a carbanion over here. So what will be the stability order? Okay, first thing, we'll see what is the order of these carbanions. So this is, I think, the primary one, and this is the secondary one, and this is the tertiary one, right? Because we take this whole group as a one group, alkyl, and here you find there are two alkyl groups. Okay, here you find there are three alkyl groups for this particular carbanion. So this is tertiary, and we know the order of stability for the carbanions is 1 degree is more stable than secondary than tertiary, right? We know the order of stability, that is 1 degree is more stable than secondary than tertiary. So therefore here the case will be A is more stable than B than C. Very simple. Okay, let's take another example here. Let's take another question here. For example, okay, let's write it like this. We have a CCl3, the carbon with the 3 chlorine atoms, and then we have the CHCl2 right here, and then we have the CH3 here. Again, the difference here is that we have electron withdrawing groups here, electron withdrawing groups. Here are the 3, here are the electron withdrawing groups. So that means, and first one does not have electron withdrawing group, so that means the A and the B are more stable than the C. Among the A and the B, there are 3 chlorine atoms here, here's the 2, here are only 2 chlorine atoms, 3 electron withdrawing groups, 2 electron withdrawing groups. Higher the number of electron withdrawing groups, more will be the stability. So that's why A is more stable than B and then C. So this is the decreasing order of the stability. Right? Let's take one more question here. Say we have a carbanion like this. Okay, we have a carbanion like this. Let me write it. The chlorine over here and the carbanion is over here. And another example. Negative charge is over here and the chlorine is over here. Fine. So what will be the stability order? You know, this is secondary carbanion and this is also secondary carbanion. The number of carbon atoms is also same, right? The total number of carbon atoms is same in the molecule. So, and there is one electron withdrawing group, chlorine in both cases. But in this case, the electron withdrawing group, the chlorine, is a little bit more closer, right, to the carbanion. Here it is away from the carbanion, right? It's a little bit away from the carbanion. So therefore, the effect will be more here, because we know the inductive effect, you know, operates along the whole length, but it is effective when it is closer, right? Okay, so electron releasing, electron withdrawing groups here, it will withdraw electrons more, while as here on this one its effect will be less, very less, right? So that's why electron withdrawing groups, we know they increase the stability, so that's why the A will be more stable than B. If electron releasing groups are closer, they'll have a dominant effect, right? More effect. Okay, great. Next question, let's take this one as an example here. Negative charge here, and let's take another example like this, and then the third one is it's like this. We know that this one is a primary, this one is also primary carbanion, this one is secondary, and there's one more difference, that in the first one you have a conjugate system, you know, carbon, then a single, then a double bond. So this is the conjugate system, right? So at alternate positions, right, we have a single and an electron pair, so that can undergo resonance. So there, that means in the first one resonance is possible, right? So electron pair will be, it will shift in the direction, it will go here, so resonance is possible in this case. So you can delocalize the negative charge over here, and you get a double bond here and the negative charge here, and it goes back down, it goes up here, and you get the first one back. But there's no resonance, you know, there is no such resonance possible in the B and the C. In both cases, right, we do not find any resonance. So that's why we can say the A is the most stable one, right? So the A is the most stable one. Among the B and the C, you see the first one, the B is 1 degree, the C is secondary, right? And therefore, we know the 1 degree is more stable than the secondary, therefore the B is more stable than the C. Right, pretty simple. Okay, hope you got the concept. See you in the next video. Bye.